Hi everybody, hope you're doing well. Today we are going to continue our notes in chapter 18. So we've already talked about delta H, delta S, and delta G on how to determine the spontaneity of a reaction. So now we're going to go into collision theory and reaction kinetics or rates. And so we are focusing now on spontaneous reactions. So reactions that we do know are favorable and that are going to occur without outside intervention. We've been kind of talking about collision theory throughout the year and saying that in order for a chemical reaction to occur, the particles in the reactants need to collide together. And that's why, for example, we didn't really focus on solids much. It was always about solutions or gases, because those particles collide a lot more, so they can cause reactions, whereas solids kind of vibrate in place, they don't really collide. So collision theory basically says that particles need to collide in order for a reaction to occur. Now, even though if you put two reactants together, their particles are constantly colliding, only a small fraction of those collisions actually produce a reaction. Why is that? Well, think of clay clumps that we're throwing together. So think of a clump of clay sitting on a table, and you have another clump of clay in your hand, and you're trying to get them to attach together. So you throw the clay that's in your hand onto the clay that's on the table. Well, in order for them to stick together, two things have to happen. First of all, you have to aim right. If you throw it and it goes somewhere else, there's no way, of course, that they're going to stick together. But also, you have to throw it with enough force that it makes the two clumps kind of stick together. And so those are the two criteria for an effective collision. So if you look at the next slide here, collisions must have two things in order for them to be considered effective collisions. Effective collisions are the ones that actually produce a chemical reaction, not all collisions. And so, again, the particles must have enough energy to produce a reaction. So if you remember from our energy diagram, if I have, let's say, the potential energy here in time, and let's say it's an endothermic process. Your activation energy is from where the reactants are to the top of the hill. Right here. What that means is that those reactant particles need to collide with enough energy to surpass this activation energy barrier. So if they collide together with this much energy, then they fall back down and reform the reactants. Collide with this much energy, they go back and reform reactants. Collide with this much energy, then, since they've surpassed the activation energy barrier, now that they form the transition state, and now they can actually turn into products. And so they must have enough kinetic energy, again, to equal or exceed the activation energy barrier. The other criteria is that they must collide with the correct orientation. So as I said, if you throw your clump of clay and you don't aim right and it goes somewhere far away from the other one that was on the table, they're never going to attach together. And so when the particles collide, they have to collide with the correct orientation, with the correct positioning of the particles in order for the correct bonds to break, so that you go from reactants to the transition state and then to the products. So collision theory or collision model explains why some reactions are naturally slow and others are fast. So for example, carbon and oxygen, when they react together and you burn the carbon, you burn charcoal, it's a spontaneous reaction. However, if you have some charcoal sitting there and you have lots of oxygen sitting in the air, the charcoal never burns, right? And it takes a while to get it to light. If you've ever tried to get charcoal to light, it's pretty hard. Well, the reason is because that reaction, even though it is spontaneous, it's actually favored by both entropy and enthalpy, but yet it has a very high activation energy. So those charcoal, carbon, and oxygen particles are constantly colliding, but they are not colliding with enough energy to surpass the activation energy barrier. And so it takes a very long time for that reaction to occur. And so that's why you have to heat up the coal in order to get it to light, and it's kind of a hard process to do. So, like we said, some reactions, even though they're spontaneous, can happen pretty slowly, and some can happen pretty fast. If they happen fast, what does that tell us? That tells us that the activation energy is pretty small for that reaction. So a firecracker, lighting a firecracker, that activation energy is pretty small. So it's very easy to ignite, very easy to get that reaction to go. It'll go fast. Reactions that are really slow, like taking dead plants and turning them into coal, that takes years and years and years and years. That is because it has a very high activation energy. So you gotta get those particles keep colliding, and very few of those collisions are going to be effective, meaning they have the correct orientation and enough kinetic energy. So if we wanted to measure the rate, which means the speed of a reaction, well, the speed of anything, like let's say you're driving to school and you're trying to measure your speed, well, you measure whatever is changing over change in time. So when you are driving, you measure your change in distance over time. In a chemical reaction, obviously, we don't have a change in distance, but we do have a change of concentrations. I start out with my reactants, and as the reaction progresses, my reactant concentration goes down, and I start forming products, so my product concentration increases. So that's how we measure the reaction rate. It is expressed in the amount of reactant or product really changing per unit time. So let's take a look at some factors that affect the reaction rate, the rate of reaction, how fast it happens. So again, we are talking about reactions that are spontaneous, that are meant and favored to happen. But even if you have a spontaneous reaction, it could happen very slowly or it could happen very fast. The main reason has to do with activation energy. So looking at the same reaction, how can I make it slow down or speed up for the same type of reaction with the same amount of activation energy? Well, there are 4 factors that affect the reaction rate. And if you look at page 16 of your packet, we were supposed to do a rates of reaction lab. So we're going to kind of like read through it real quick together and talk about it. And so if you look at page 16 again, for your reaction rate lab, there are 4 parts because there are 4 factors that affect the reaction rate. The first one is temperature. So we're going to fill 2 beakers halfway with water, and we are going to heat one of the beakers, and the other one we're going to leave it at room temperature. And in 2 test tubes, we are going to put some potassium permanganate, and we are going to add 2 milliliters of oxalic acid. Potassium permanganate is a very light, if you dilute it enough, it's like a light purple or a light pink. And when you add oxalic acid, it turns colorless. So you do that in 2 test tubes. One of them you put it in the room temperature water, and the other one you put it in the hot water bath. And you see how long it takes for it to go from pink to colorless. And you will see that the one that is heated goes much faster. So let's talk about why that is in terms of collision theory. So temperature is the first factor that affects the reaction rate, and if you increase the temperature, you increase the rate of the reaction. It makes it go faster. Why is that? Well, remember that reactions happen with collisions, and only effective collisions cause chemical reactions to occur. For an effective collision to happen, you have to have the correct orientation. You also have to have enough energy that those particles are colliding to equal or surpass the activation energy barrier. So if you raise the temperature, that means your particles are moving faster and with more kinetic energy. So when they collide together, they are colliding with more kinetic energy, and so more of those collisions would equal or exceed the activation energy barrier. So here again is my potential energy diagram here. Time, reactants, products, transition state. And so my reactants here collide. They need to collide with at least this much energy. And so if the temperature is higher, particles are moving faster with a lot of kinetic energy, and so more of those collisions would equal or surpass this activation energy barrier. So more of my collisions are effective, and therefore the reaction would occur faster. The next one is, we're going to skip to part D of the lab if you are looking at page 16, which is particle size or surface area. So for this part of the lab, you were supposed to obtain 2 beakers. You fill them with the same amount of water. And in one of them, you put a whole Alka-Seltzer tablet. In the other one, you break up an Alka-Seltzer tablet into small pieces and then put it in there. And as the Alka-Seltzer tablet is placed in water, a chemical reaction occurs, and one of the products is CO2. So you see bubbling occurring. And you will see that the reaction is much faster when you break up the Alka-Seltzer tablet into pieces compared to when it's whole. And so the the factor there is particle size or surface area. So the smaller pieces have a higher surface area. And so increasing the surface area increases the rate of a reaction. Let's think about why that is in terms of collision theory. So again, collision theory says that for a reaction to happen, you have to have an effective collision, which means correct orientation and enough kinetic energy. Well, if you have a lot of surface area, that means a lot of your particles are exposed to the surface and they're able to collide, and so they can collide faster and therefore cause a faster chemical reaction. Compared to the whole tablet, the surface particles would react, and then that exposes some more, and then exposes some more, and then exposes some more. So it takes much longer for the core molecules to actually react. Next factor is concentration, and again, if you are looking at your lab on page 16, that would be part C. So for part C, you take 3 test tubes. In one of them, you put 0.5 molar HCl. In another, you put 1 molar HCl. And in the third one, you put 3 molar HCl. So same volume, but different concentrations of the HCl. And to each of them, you put a tiny piece of magnesium ribbon in there. And you observe magnesium and HCl react. You get magnesium chloride, which is a salt that's soluble. And you also get some hydrogen gas, which bubbles. And you observe the reaction. If you were to do it, you would see that the one in the 3 molar, the one that's really concentrated, reacts much faster than the one that's in 1 molar, and then the one that's 0.5 molar is very, very slow. And so our factor here is concentration. If you increase the concentration of the reactants, that usually means that the rate of the reaction increases. Why is that in terms of collision theory? Well, if your concentration, the amount of solute in a given area, is higher, that means that you're going to have more particles in a given volume, and so those particles are more likely to collide. Since there's more of them, more collisions, and therefore more effective collisions. So your reaction will happen faster. And then finally, presence of a catalyst increases the reaction rate. If you look at our lab on page 16, that was part B. You take some hydrogen peroxide. Hydrogen peroxide will naturally decompose into water and oxygen, but it happens super, super slow. That's why hydrogen peroxide at home comes in a brown bottle, because light will actually catalyze that reaction. It'll make it go faster. And so there are many different ways to add a catalyst to this. When we did our rocket lab with thermochem, we used manganese dioxide as a catalyst for this reaction. In biology, you probably have used like chicken liver or something like that as a catalyst for this reaction. In this lab, we would have used a piece of potato that has some enzymes that act as a catalyst for this reaction. You'd see that it starts bubbling, giving off oxygen gas much faster. And so presence of a catalyst increases the rate of reaction. So let's talk about why that is and what is a catalyst. So I know you've talked about catalysts before in some other science classes, but let's review that. So a catalyst is a substance that speeds up the reaction, but without being consumed itself in the reaction. So that's the main difference between a catalyst and a reactant. We saw that if you increase the amount of reactant, you're going to get a reaction that goes faster, right? But the reactant gets consumed. A catalyst speeds up the reaction, but without being consumed. So it's a substance that speeds up the reaction without being consumed. How does it do that? It does that by lowering the activation energy, and we'll see what that looks like. Just for fun, a couple of terms here that you probably have heard of before. An enzyme is basically a biological catalyst. It's a catalyst that is a biological molecule. And then an inhibitor is something that interferes with the action of a catalyst. So let's focus more on how the catalyst works. And so different catalysts work in different ways, but all of them basically take a different pathway to the reaction. And when they do that, they lower the activation energy. So let's take a look at this energy diagram here. So there's your potential energy. This is the time of the reaction or reaction progress. And this looks like an endothermic reaction here. That's the black. This pink shows you the activation energy. So how much energy you have to give the reactants in order to get to the transition state. So it's this much. So what we're saying is these reactants have to collide with enough energy to surpass this activation energy barrier, right? They have to collide with this much energy or more. Now, when you add a catalyst, what happens is the pathway changes. So it changes basically the transition state. So now this is your new transition state. And so here's your new reaction pathway going through that green. And so because your transition state changed into a species that is a little bit more stable, lower in energy, now your activation energy is much lower. So again, activation energy is from where your reactants are to the top of the hill, where your transition state is. So now compare the amount of the green versus the pink there, or magenta. So when these particles collide in the reactants, they only need to surpass this much energy. And so more of your collisions that would happen normally are effective because more of them can surpass the activation energy barrier compared to what it was before. Let's look at an exothermic reaction. Same idea. So a catalyst works by lowering the activation energy barrier. And so normally, as the reaction is progressing, this is how much energy I need to give it in order to, or not give it, but it's how much energy needs to be surpassed in order for the reaction to occur. And so comparing that to the new pathway with the catalyst, which is the green, now that's the amount of energy that I need to surpass. And so more of your collisions of reactants will surpass this barrier compared to this barrier. And so your reaction will occur faster. All right, next time we will talk about reversible reactions and equilibrium.